To better help us understand the natural exponential function and why it's so important, we first need to consider the graph of some common exponential functions, base A. So that's what we're going to do here. To begin, we want to consider the graphs of the following exponential functions. So we have the exponential function base 2, or y equals 2 to the x. We have the exponential function base 4, or y equals 4 to the x. And we have the exponential function base 10, or y equals 10 to the x. So to consider the graphs of these exponential functions, let's start by creating a table of values. And then we'll plot the points. So for each table of values, I'm going to use the same x values. Let's go with x equals -1, 0, and 1. So the first function we are considering is y is equal to 2 to the x. And then we'll have our column for the ordered pairs x, y. And so since we're using these same x values, I'll do a little squiggly line here so that we can consider the next exponential function, y equals 4 to the x. And we'll consider the ordered pairs that this creates. And another little squiggle line here to differentiate between the functions. Last but not least, we have y is equal to 10 to the x. And we'll have a column for its corresponding ordered pairs. Beautiful. So, starting with y equals 2 to the x. When x equals -1, we have 2 raised to the -1, which is equal to 1/2. So you have the ordered pair -1, 1/2, or 0.5. When x equals 0, we have 2 to the 0, which equals 1. So we have the ordered pair here, 0, 1. And last but not least, when x equals 1, we have 2 to the 1, or 2 to the first, which leaves us with 2, giving us the ordered pair 1, 2. So moving on to our second exponential function, when x equals -1, we have 4 to the -1, or 1/4. So the corresponding ordered pair here is going to be -1, 1/4. When x equals 0, we have 4 to the 0, which is 1. So again, we have that ordered pair 0, 1. And last but not least, when x equals 1, we have 4 to the first power, or just 4. Last but not least, we are considering the exponential function y equals 10 to the x. So when x equals -1, we have 10 to the -1, which is 1/10. When x equals 0, we have 10 to the 0, which equals 1. And then when x equals 1, we have 10 to the first, which is just 10. So we have the three ordered pairs, -1, 1/10, 0, 1, and 1/10. So we now want to go ahead and take these functions, or take these ordered pairs, and sketch a graph. So here we go. We have our beautiful y-axis, and we have the x-axis. So say there is -1, here is 0, and here is +1. And then we'll do a 2x2 scale for y. So we can say here's 2, 4, 6, 8, 10. So plotting our first function, y equals 2 to the x, we have the ordered pair, -1, 1/2. So if there's 1, then 1/2 is right about there. So there's our first ordered pair. We then have the ordered pair 0, 1. And last but not least, we have the ordered pair 1, 2. And so connecting these three ordered pairs with a smooth curve, we can see the graph of the exponential function. So this is y equals 2 to the x. The next function that we are considering is y equals 4 to the x. So we have the first ordered pair, -1, 1/4. So right about there, we'll say. We have 0, 1, so that same point. And then our third ordered pair is 1, 4. And again, connecting these ordered pairs with a smooth curve, we see the graph of the exponential function y equals 4 to the x. And last but not least, we have y equals 10 to the x. So this first ordered pair is negative 1, 1/10. So way down here. The next ordered pair is still 0, 1. It's that same point. And last but not least, we have the ordered pair 1, 10. So all the way up here. And again, connecting these three ordered pairs with a smooth curve, we attain the graph of the exponential function y equals 10 to the x. So looking now at the graphs of these three exponential functions, we can make the following observations. So the first thing that we're observing here is that the graphs of the exponential functions y equals a to the x gets steeper as the base a gets larger. So if we're looking at our graph, we can see that the steepest graph has the largest base. Now, the idea of steepness is conveyed by the slope of a tangent line to the graph at a point. Now, tangent lines to graphs of functions are not defined precisely until the beginning of Calculus 1, but intuitively, the tangent line to a graph at a point is a line that just touches the graph at that one single point. So I want you to keep this intuitive understanding of a tangent line in mind as we transition to compare these common exponential base a's to the natural exponential base e. The most important exponential function for modeling natural, physical, and economical phenomena is the natural exponential function. Now, this natural exponential function is an exponential function, or y equals a to the x, but specifically whose base a is a special number. And that special number is e. So if we were to take our calculators and plug in e and hit enter, we would see that e is approximately equal to 2.7182818828 la 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 la. So it keeps going on forever. This is an irrational number. So a real number that never terminates and never repeats. Now, while this number e may seem a little strange right now, this number is going to continue to simplify our computation for exponential growth and exponential decay models as we progress through calculus. And why or how, you might be asking yourself, which is a great question. So the property of the number e that makes this number so useful in calculus is that the graph of the natural exponential function y equals e to the x has a slope of 1 when it crosses the y-axis. So again, the advantage of using the number e as the base for your exponential function is that it simplifies many of our exponential calculations throughout our calculus careers. Now, to better understand this property, let's go ahead now and compare the graph of the natural exponential function to the graph of two of the common exponential functions that we just looked at, and use a tangent line at the point 0, 1 to see the slope. So for the following graphs, we are going to use tangent lines to show that the slope of each graph of the exponential function y equals a to the x as it crosses the y-axis. And we're going to use several different values of a to demonstrate this. Now, before we begin, I want you to recall that at the beginning of this video, we saw that the graphs of the exponential functions get steeper as their base gets larger. And so we're going to convey this steepness by considering the tangent line for each graph. So in case 1, we are considering an exponential function base 2, or y equals 2 to the x. So our point of tangency is the point where this graph is crossing the y-axis. So that's the point 0, 1. So intuitively, we know that a tangent line is a line that touches the graph at just this point. So here we go. Here is our tangent line that touches the graph at just that point. Beautiful! Now in case 2, we are considering an exponential function of base e, so the natural exponential function. And again, our point of tangency is the point where this graph crosses the y-axis, so 0, 1. So sketching our tangent line so that this line just touches the graph at that single point. Lovely! And last but not least, in case 3, we are considering an exponential function of base 4, or y equals 4 to the x. And again, our point of tangency is where this graph is crossing the y-axis, so that point 0, 1. And drawing our tangent line to this point here. Beautiful. So, looking at these 3 graphs, again, notice that as the base of the exponential function gets larger, the graph of the exponential function gets steeper, which we can now more clearly see by observing the tangent lines at these points. So, looking at case 1 here, our tangent line at the order pair 0, 1. This tangent line has a slope that is defined by the natural log of 2, which is approximately equal to 0.7. Now, if we wanted to calculate the exact value of the slope of the tangent line by hand, we would need to use the limit of the difference quotient as an arbitrary h approaches 0, and then evaluate the result at x equals 0. So I'll leave that up to you, and we'll take advantage of that this is the exact slope of the exponential function y equals 2 to the x as the graph crosses that y-axis. Now, looking at case 2, where we're considering the natural exponential function, this tangent line has a slope of 1. And looking at the tangent line in case 3, for the exponential function y equals 4 to the x, this tangent line has a slope defined as the natural log of 4, which is approximately equal to 1.4. Beautiful! So let's quickly now summarize what we're observing here with these 3 exponential graphs. So the first thing I want you to notice is that the slope is exactly equal to 1 when base a equals the number e. Now, the second thing we want to notice is that the slope is smaller than 1 if the base a is less than e, as we're seeing with the exponential function y equals 2 to the x. And last but not least, we're observing here that the slope is going to be larger than 1 if the base a is greater than e, as we're seeing with the exponential function y equals 4 to the x.